Welcome to The Explainer. Today, we're going to pull back the curtain on the hidden science that connects a fizzy soda, a winter-proofed car, and even the cells inside your own body. It's all about the chemistry of solutions, and believe me, it is everywhere. Okay, let's kick things off with a few everyday mysteries you've probably wondered about. First up, that amazing fizz from a can of soda. Why is it so intense right when you crack it open, but then it just disappears?
Or, picture this. It's a freezing winter day. How is it possible that just adding something simple like salt to a road or antifreeze to your car's radiator can completely change the rules and stop water from turning to ice?
And hey, this isn't just about cars and roads. This same science is literally happening inside you and me right now. What's the secret that keeps our red blood cells perfectly balanced so they don't swell up like a balloon or shrink down to nothing?
Well, the common thread connecting all of these puzzles is the powerful and honestly super elegant chemistry of solutions. It's the science of what happens when you mix stuff together, and it explains the whole shebang.
So to really get our heads around these mysteries, we need to put on our chemist hats. And the first step is to get familiar with their toolkit, specifically how they measure exactly what's inside a mixture.
It really boils down to two words that sound almost identical: molarity and molality. Now, molarity is all about volume. But molality, that one's all about mass. And that difference is absolutely crucial, because when things heat up, they expand, right? Their volume changes, but their mass, that stays the same no matter what.
Okay, so think about that for a second. If volume changes with temperature, but mass doesn't, which one of these do you think is going to be more reliable for any experiment that involves a temperature change?
Bingo! If you said molality, you nailed it. Because mass is constant, molality gives scientists a rock-solid, stable measurement when they're studying things like boiling points and freezing points. For accuracy, it's the undisputed champ.
All right, with our chemist toolkit sorted, let's get into the really cool part. Let's look at what happens when you just add stuff to a liquid. You can fundamentally change its behavior, making it way harder for it to escape as a gas.
It all starts with something called the surface barrier effect. Imagine the surface of the water is like a super crowded doorway. Now you add a solute that doesn't like to evaporate, like sugar or salt. Those particles just hang out at the surface, getting in the way, basically acting as roadblocks. It physically blocks the water molecules from leaving. Fewer escapees means lower vapor pressure. Simple as that.
Now, this whole idea of pressure gets really important when we start talking about dissolving a gas into a liquid. And for that, there's a basic rule of the road called Henry's Law, which tells us that the pressure of a gas is directly linked to how much of it you can cram into a liquid. And boom, this brings us right back to our soda can mystery. Inside that sealed can, there's a ton of pressure, forcing all that carbon dioxide gas to dissolve. But the second you pop that top, psst, the pressure is gone. The CO2 is no longer forced to stay dissolved, and it makes a run for it, escaping as bubbles. And that, my friends, is your fizz.
Okay, so that's gases and liquids. But what about mixing different liquids together? Well, that's when things get even weirder, because it turns out not all mixtures play by the rules.
You see, in a perfect world, in an ideal solution, all the different molecules get along just fine. Their attraction to each other is about the same as their attraction to themselves. But the real world is messy. Sometimes the new mix has weaker attractions. That's a positive deviation. This makes it easier for molecules to escape. Other times, the new attractions are way stronger, a negative deviation. And that holds the molecules in a death grip, making it harder to escape.
And when these deviations get really extreme, something bizarre happens. You get a mixture that starts acting like it's one single pure substance.
They're called azeotropes. A mixture with a big positive deviation can actually boil at a temperature lower than either of the pure liquids you started with, and one with a big negative deviation can boil at a temperature higher than either. How wild is that? It means you can't separate them by normal boiling or distillation because they just evaporate together. They're stuck.
Okay, get ready for this, because this next part is a real game changer. For some of the most powerful effects we've been talking about, it doesn't even matter what you add. The chemical identity is irrelevant. All that matters is how many particles you throw in.
This is where we enter the world of what are called colligative properties. And the rule here is so simple. It's not about what the particles are, it's about how many there are. It's just a counting game. And we can actually put a number on this multiplier effect. It's called the Van't Hoff I factor. So look, glucose, or sugar, dissolves as one particle. Its I factor is 1. But regular old table salt, NaCl, splits into 2 ions when it dissolves. That means it has twice the effect, twice the power of sugar. And then look at aluminum chloride. It splits into 4 particles. That gives it a massive impact.
So what does all this counting get you? Well, you get 4 incredible superpowers. By just adding particles, you can lower the vapor pressure, you can raise the boiling point, you can lower the freezing point, and you can control something called osmotic pressure. It's all about the numbers.
And just like that, everything clicks into place. All those questions we started with, we've got our answers. The salt on the roads and the antifreeze in your car, they work by cramming particles into the water to lower its freezing point. And our red blood cells, they stay balanced because of osmosis, which is driven by the number of particles inside and out. It's all colligative properties in action.
Okay, let's take what we've learned and tackle one more real-world puzzle. Deep-sea divers breathe a special mix of gases. Why on earth do they use expensive helium instead of just, regular air?
And the answer is a life-or-death application of Henry's law. Under the intense pressure deep underwater, nitrogen from the air would dissolve in a diver's blood. If they surface too quickly, that nitrogen comes rushing out as bubbles, causing a condition called the bends, which is incredibly dangerous. Helium is way less soluble, so it doesn't build up, making the trip back to the surface much, much safer.
All right, so I've got one last brain teaser to leave you with. We've seen how salt can split into 2 particles, right? An I factor of 2. But what on earth would it mean if a substance actually had an I factor of less than 1? Say 0.5. It's not splitting apart. It must be teaming up. What kind of chemistry could make that happen? Something to chew on. Thanks for joining us.